We'll start in 1 minute. Today we'll be in section 11.3. That's the section on the integral test and estimates of sums. Determining what a convergent infinite series converges to is generally more difficult than determining whether an infinite series is convergent or divergent. Under ideal conditions, the integral test can be used to determine if a series is convergent or divergent. So here's the integral test as it's stated in the textbook on page 721. Suppose a function f is continuous, positive, and decreasing on the interval from 1 to infinity, and let a sub n be equal to f of n, where n is a positive integer. Then the series of the a sub n terms, as n ranges from 1 to infinity, is convergent if and only if the improper integral of f of x dx from 1 to infinity is convergent. So that is, if the improper integral of f of x dx from 1 to infinity is convergent, then the corresponding series of the a sub n terms is also convergent. On the other hand, if the improper integral of f of x dx from 1 to infinity is divergent, then the corresponding series of the a sub n terms is also divergent. Okay, that's a pretty nice test, but keep in mind it can only be used if the conditions of the function f are satisfied. The function f must be continuous, positive, and decreasing. And then a sub n has to be equal to f of n. One thing, if the function f is not decreasing to begin with, but is eventually decreasing past a certain point, then the integral test can be used in those cases. Okay, we'll just discuss the integral test by drawing some graphs here. Let's let f be a continuous, positive, and decreasing function on the interval from 1 to infinity with a sub n equals f of n. In the first case, we consider when the improper integral of f of x is convergent. Okay, so we'll sketch a graph in the xy plane where f of x is positive, continuous, and decreasing. And we'll plot a few of the positive integers on the x-axis. Okay, so we'll construct a few rectangles. The area of this first rectangle is a sub 2. So this is the graph of y equals f of x. We'll put in another rectangle. The area of this one on the left is a sub 1 because the height of the rectangle is a sub 1. And then this rectangle, the area, this one is a sub 2, this one is a sub 3, and so on. And we're going to begin by focusing on the areas of the second, third, fourth, and so on rectangles. So on the interval from 1 to infinity, notice that a sub 2 plus a sub 3 and so on is less than the integral from 1 to infinity of f of x dx, because those rectangles are below the graph of y equals f of x. So if this improper integral is convergent, then the sum of the terms from the sequence a sub n from a sub 2 to infinity is also convergent. Well, we're missing one of the terms, a sub 1, but all we have to do, first note that this improper integral, since it's convergent, it's equal to some finite number m. So if we just add a sub 1 to all three parts, the full series is less than a sub 1 plus the finite number we get from the convergent improper integral. So this is a sub 1 plus m. So by comparison, this shows that the infinite series from n equals 1 to infinity of the a sub n terms is convergent. It's convergent when the improper integral of f of x from 1 to infinity is convergent. So hopefully this picture is convincing. Okay, in case 2, we suppose that the improper integral of f of x from 1 to infinity is divergent. So we'll draw another graph of a continuous decreasing positive function y equals f of x. And we'll label a few of the positive integers, 1, 2, 3, 4, 5, and so on. Okay, this time we'll construct triangles that are partially above the graph of y equals f of x. So this first rectangle from 1 to 2, the area of this one is a sub 1. The area of the second rectangle is a sub 2, and so on. Okay, so in this picture, when we compare the areas of the rectangles with the area that's below the graph of y equals f of x from 1 to infinity, this time we see that the improper integral from 1 to infinity of f of x dx is less than the series from n equals 1 to infinity of the a sub n terms. But since the improper integral is convergent and it's less than the infinite series, that has to mean that the infinite series is also divergent. So since the improper integral of f of x dx from 1 to infinity is divergent, then the infinite series is also divergent. Yeah, let's move on to the next page. If p is a fixed real number, then a series of the form, this form, the terms are 1 over n to the p as n ranges from 1 to infinity. This is called a p-series. So in a p-series, n ranges from 1 to infinity, but the exponent p is the same for each of the terms. And we'll discuss for which values of p a p-series is convergent. When p is less than or equal to 0, then the limit of 1 over n to the p as n approaches infinity does not equal 0. So this is a fact that you learned in Calculus 1. You can just pick a few p-values less than or equal to 0, and then if necessary, you can remind yourself that the limit of 1 over n to the p does not equal 0. So that means the p-series that correspond to p less than or equal to 0 are divergent by the test for divergence. If p is greater than 0, then f of x equals 1 over x to the p is continuous, positive, and decreasing on the interval from 1 to infinity. So the integral test can be used to test for convergence in those cases when p is greater than 0. Okay, but already this semester we've learned about those types of integrals from section 7.8. We recall that the improper integral of 1 over x to the p dx from x equals 1 to infinity is convergent if p is greater than 1, and it's divergent if p is less than or equal to 1. So when we apply the integral test for the corresponding p-series, we get this result. The p-series of 1 over n to the p as n goes from 1 to infinity is convergent if p is greater than 1 and divergent if p is less than or equal to 1. Okay, so we have an example of a p-series. In this one, 1 over the cube root of n to the 4th as n ranges from 1 to infinity. The directions here say to use the integral test to show that this p-series converges. So we can rewrite the terms in this infinite series. Instead of 1 over the cube root of n to the 4th, we can write it as 1 over n to the 4/3. So if this were just a question, is this p-series convergent? Then we could look at the value of p. We could see that it's greater than 1, and we would just use the result above. Yeah, since the p-value is greater than 1, this series converges. But if we're going to use the integral test to show that it converges, then we have to do a little bit more work. Okay, so in using the integral test, we want to show that the integral from 1 to infinity of 1 over x to the 4/3 dx show that this converges. It's already been alluded to, but we'll just make a note that the function f of x equals 1 over x to the 4/3, which can be thought of as x to the negative 4/3. Note that it's continuous, positive, and decreasing on the infinite interval from 1 to infinity. Hey, it's pretty easy to tell that it's continuous. It's also easy to tell that for x values from 1 to infinity that it's positive. How could you show that it's decreasing? Or what argument would you give to say that this function f of x equals x to the negative 4/3 is decreasing?
As x gets bigger, the denominator gets bigger, so the number gets smaller.
Say that again?
As x gets bigger, the denominator gets bigger, so the number gets smaller.
Hey, that's an argument. What about a calculus argument? Well, it's not too hard to show that the first derivative, which is negative 4/3 times x to the negative 7/3, the first derivative is negative for all values of x from 1 to infinity. And when the derivative of a function is negative on an interval, it means the original function is decreasing because the rates of change are all negative. Okay, but moving on, let's rewrite this improper integral as a limit. I'll use the number or the letter b as b goes to infinity of the definite integral from 1 to b of x to the negative 4/3 dx. Okay, an antiderivative of x to the negative 4/3 is x to the negative 4/3 plus 1 divided by negative 4/3 plus 1 from 1 to b. Okay, negative 4/3 plus 1 is negative 1/3. If we divide by negative 1/3, that's equivalent to multiplying by negative 3. And I'll go ahead and, okay, so it's negative 3 times 1 over x to the 1/3, because x to the negative 1/3 is 1 over x to the 1/3 from 1 to b. Okay, so negative 3 over b to the 1/3, and then minus negative 3 times 1 over 1, or just times 1. So as b goes to infinity, this denominator goes to infinity, so this term goes to 0. Negative 3 over b to the 1/3 goes to 0, and then plus 3. So since the improper integral converges, the infinite series also converges. Make sure that you catch this next comment. The improper integral converges to 3, but we don't know what the series converges to. We just know that it's convergent. Okay, in the next example, use the integral test to show that this series, arctangent of n over 1 plus n squared as n goes from 1 to infinity, show that that converges. Use the integral test. Well, if we're going to use the integral test, we have to show that the function f of x, which is the arctangent of x over 1 plus x squared, we have to show that it's continuous. It's pretty obviously continuous. For x values from 1 to infinity, arctangent is positive and the denominator is positive. The only thing that might be a challenge is to show that this function is decreasing or decreases on the interval from 1 to infinity. So if we can show that the first derivative is negative on the interval from 1 to infinity, that means the function f is decreasing on that interval. Okay, so to take the derivative of f of x, we can apply the quotient rule. The derivative of arctangent of x, so remember the quotient rule for derivatives. We compute the derivative of the numerator, multiply that by the denominator, then we subtract the numerator times the derivative of the denominator, and then divide by the denominator squared. So the derivative of arctangent of x is 1 over 1 plus x squared. We multiply that by the denominator, 1 plus x squared. Then we subtract what's in the numerator, arctangent of x, multiplied by the derivative of the denominator, which is 2x. And then we divide it all by the square of the denominator. So 1 plus x squared squared. Over here, 1 over 1 plus x squared times 1 plus x squared is 1. So we get 1 minus arctangent of x times 2x divided by 1 plus x squared squared. All right, so for x values from 1 to infinity, arctangent of 1 is pi over 4. And pi over 4 times 2 times 1, well, that's pi over 2. Pi over 2 is bigger than 1, so it's negative. And arctangent increases from x to infinity, so this is always negative. So this is negative for x greater than or equal to 1. Okay, then to use the integral test, we just compute the improper integral from 1 to infinity of arctangent of x over 1 plus x squared dx. If we use u substitution, u equals arctangent of x, then du is 1 over 1 plus x squared dx. So we have all of those appearing in this integrand. So we can transform the integral so that it's just u du. And then what about the limits of integration? When x is 1, u is the arctangent of 1. The arctangent of 1 is pi over 4. And as x goes to infinity, what does arctangent get close to? Pi over 2. I can draw a picture of arctangent of x in a minute, but anyway, we just have this pretty simple integral to evaluate. The integral of u du is u to the second over 2. Evaluate that from pi over 4 to pi over 2. I'm about out of space, but I think you can do the rest on that one. So this is going to be a finite number. So by the integral test, this infinite series converges. So real quick, a graph of y equals arctangent of x. So on the interval, from negative pi over 2 to pi over 2, if we were to graph y equals tangent of x, we can use infinitely many intervals, but when we're interested in matching an interval with the arctangent, we use the interval from negative pi over 2 to pi over 2. So y equals tangent of x looks like this, and its inverse will have horizontal asymptotes at y equals pi over 2 and negative pi over 2. And so the graph of y equals arctangent of x looks kind of like this. So as with all graphs of one-to-one functions and their inverses, you can think of taking the graph of tangent of x, lift it up, and then lay it down this way, and you get the graph of the inverse. Okay, let's move on. And now we will look at how to estimate the sum of a convergent infinite series. Okay, we let f of x be a continuous, positive, decreasing function such that f of n equals a sub n for each positive integer n. And suppose that it has been shown by the integral test that the infinite series of the a sub n terms is convergent, and that the infinite series of the a sub n terms converges to a finite number s, which is the limit of the s sub n sequence, where s sub n is equal to the sum of the first n terms from the a sub n sequence. This is the sequence of partial sums. Okay, so in that setting, for each positive integer n, an approximation of the infinite series of the a sub n terms is s sub n. And so that is one of the uses of the sequence of partial sums, is to approximate the infinite series. Okay, well, we have a new entity. The remainder of the approximation s sub n is defined to be capital R sub n, which is equal to s minus s sub n, which is just a sub n plus 1 plus a sub n plus 2, and so on. And another word for the remainder of the approximation is that it's the error made when s sub n is used to approximate the sum. Okay, so we note that we have this inequality. The improper integral of f of x dx from n plus 1 to infinity is less than or equal to the remainder r sub n, and at the same time, the remainder r sub n is less than or equal to the improper integral of f of x dx from n to infinity. So we'll illustrate this. It might not be obvious from the foregoing comments. So we'll draw a couple of graphs that might be convincing. Okay, so suppose we start at n and go to n plus 1, then n plus 2, and so on. Oops, that's n plus 3. So first we'll look at rectangles that are below the curve. The length of each one of these subintervals is 1, going from n to n plus 1 is 1 unit, and so on. And this is the graph of y equals f of x. And also remember that f of n is equal to a sub n. So the area of this first rectangle on the left, the area of that is a sub n plus 1, because the height is determined by n plus 1. The area of the next rectangle is a sub n plus 2, and so on. So in this picture, the sum of the areas of the rectangles, a sub n plus 1 plus a sub n plus 2, and so on, it's less than the improper integral starting from n and going to infinity. Okay, but a sub n plus 1 plus a sub n plus 2 and so on, that's just the remainder r sub n. So we get r sub n is less than the improper integral from n to infinity of f of x dx. So that's what the right side of this compound inequality says. The remainder r sub n is less than or equal to the improper integral of f of x dx from n to infinity. Okay, to show the other inequality, we'll draw another picture. So here's y equals f of x again. This time we'll start at n plus 1 and then to n plus 2 and so on. This time we'll construct rectangles that are partially above the curve. The area of this first rectangle is a sub n plus 1 because the height of that rectangle is determined when x is n plus 1. And so on. But since the graph of f of x is below the upper portions of those rectangles, this time we have the indefinite integral starting at n plus 1 and going to infinity of f of x dx. That's less than a sub n plus 1 plus a sub n plus 2 and so on. But a sub n plus 1 plus a sub n plus 2 and so on is just what r sub n is. Okay, so that picture hopefully convinces you of the left side of this compound inequality. Okay, then we do another thing. Recall that r sub n is defined to be s minus s sub n. So s sub n is the nth partial sum. So if we add s sub n to all three parts of that compound inequality, we get this compound inequality. The nth partial sum plus the improper integral from n plus 1 to infinity of f of x dx is less than or equal to the sum of the series, which is less than or equal to the nth partial sum plus the improper integral from n to infinity of f of x dx. So perhaps you can see the use of this compound inequality. Suppose that it's really difficult to find the exact sum of an infinite series. But oftentimes improper integrals are not that difficult to evaluate. And also finding the sum of the first n terms, the sequence of partial sums, is oftentimes not difficult. So we can get really good approximations for a sum by using the sequence of partial sums and improper integrals. So we'll illustrate that perhaps in an example. So Leonhard Euler, he's a famous mathematician from 200 or 300 years ago. He calculated that this infinite series of 1 over n to the second, as n ranges from 1 to infinity, he showed that that's equal to pi to the second over 6. That number is approximately 1.64493 and so on. Okay, so what we're going to do, we're going to find the partial sum f sub 10 from the infinite series and estimate the error in using f sub 10 as an approximation to the sum of the series. So f sub 10 well, we're going to add up the 1 over n to the second terms as n goes from 1 to 10. So when n is 1, we get 1 over 1 squared is 1, and then plus 1 over 2 squared, or 1/4, plus 1 over 3 squared, which is plus 1/9, and so on, plus 1/16, plus 1/25, plus 1/36, plus 1/49, plus 1/64, plus 1 over 81, plus 1 over 100. If you add those up, this is what I included on this page. So this is approximately 1.5497677, and so on. Okay, what did we see from the previous page? So when n is 10, let's see, we have the inequality s sub 10 plus the improper integral from 11 to infinity of 1 over n to the second, or sorry, but I'm going to use x, 1 over x squared dx. This is less than or equal to the actual sum s, and this is less than or equal to s sub 10 plus the improper integral from 10 to infinity of 1 over x squared dx. So this is what we're going to do in the next step. On this one, we just want to estimate the error. The error is r sub 10. So the improper integral from 11 to infinity of 1 over x squared dx is less than or equal to the error r sub 10, which is less than or equal to the improper integral from 10 to infinity of 1 over x squared dx. These integrals are pretty easy to evaluate. So what's an antiderivative of 1 over x squared? So let's just do that here. 1 over x squared, the improper or the indefinite integral of 1 over x squared dx. That's just equal to negative 1 over x. And so if you evaluate negative 1 over x from 11 to infinity, well, at infinity, negative 1 over x goes to 0, and then we're subtracting a negative 1 over 1/11th. So we just get 1 over 11 is less than or equal to the error r sub 10, which is less than or equal to, this one will be 1/10. Okay, then if we add what S sub 10 is to both sides, down here, we'll get about 1.5497677 plus 1/11th. That will be less than or equal to the actual sum S, and that's less than or equal to 1.5497677 plus 1/10. Okay, I'll leave the rest of this for you to do. You can use a calculator to come up with decimal approximations of those. And that can be that will be a range of approximate values for S. Another thing that you could do is just take the average of the lower estimate with the upper estimate. Okay, we have a few seconds left to answer this one. We want to find a value of n so that the error is less than 0.001. So we know that r sub n is less than or equal to the improper integral from n to infinity of 1 over x squared dx. And we also know that this is going to be 1 over n. So if we want 1 over n to be less than 0.001, which is 1 over 1,000, then that means we want to pick n to be greater than 1,000 so that the error of our approximation is within 0.001. Okay, we're out of time, so go ahead and sign in for attendance.
Could I meet with you today to go over my test 3?
Say again?
Could I meet with you today to go over my test 3?
Yeah.
What time? I know you have office hours right now, but I have a class.
Yeah.
Would like 1 o'clock? Or
Should it be later? Like
I have practice at 3.
at 3?
So if but I'm free between there.
So 2 o'clock?
2 o'clock? Yeah, that works.
Just come to my office.
Awesome. Thank you so much.
Yeah.